Hi, everyone. We're about to start. So in this session, this is the dynamic session. I'm really glad everyone stayed here. This is the last session of the day. We're going to have 4 presenters, and the 2 that are actually here, I am excited for them because they finally have their work paid off and they can enjoy the rest of the conference. I'm kidding. The first paper that we have is fast position-based multi-agent group dynamics. It's by Tomer Weiss. One of the surprising things and like magical things about how the computer graphics industry is going right now is like this is one of a bunch of graphics researchers coming from Israel, an industry that didn't exist until like a decade ago. I say this because I'm from there as well. We're about to have Tomer present his work. Tomer is now a professor at NJIT. He went to school at Tel Aviv University and did his PhD in University of California. Good.
Yeah, thank you, Omer, for the nice introduction. Hope you can hear me over here. So I did my PhD, as Omer said, in UCLA. I'm going to start without much introduction. I'm very excited to be here, by the way. I would hope it will be sunny. That's my only small fix. So I'm from NJIT. We're actually right across Manhattan. That's where our office is. And this is an actual shot of the view from if you go to our campus in that tower. So it's a pretty nice campus. So I'm going to talk about, first of all, the overall problem that I'm working on, which is multi-agent crowd simulation. So in real life, you can see maybe scenes like this from some sort of Japanese train station. So you can see a lot of collective dynamics happening here, and like the stream is kind of going, and everyone is like moving towards where they want to go. But I'm going to focus on a sub-problem for this paper work today, which is group motion. So what is group motion? So most of the times, like in real pedestrian life, you don't really see much group motion. For example, this takes place in a European city, so it's pretty relaxing. People are strolling hand in hand and so on. Not much like kind of dynamics, but it's still like an interesting kind of phenomena. If you look at more kind of large scale formations and groups, you can see that more in like military style parades, like you see here. This I guess is from China. Again, like people are kind of moving in the same shape towards a certain goal. There's a certain kind of choreography here and a certain geometry for this kind of problem. We can also see the kind of on a smaller scale here, like this kind of military drills that I think this is what they do in like some sort of a U.S. Army kind of drill. So you can see people kind of working in their formation in like a training kind of regimen. So moving on towards graphics, so we can see this also happening a lot in like visual effects. So you probably may be familiar with this movie. I think it may have won a couple of awards. So this is like a battle scene from Lord of the Rings. And you can see there's a lot of group motion happening here, a lot of dynamics. And it looks kind of pretty cool as far as I can see. Also, like on a much simpler scale, like we can see this in many games, like you see here in this, I think this is Age of Empires. So there's like a formation and they're like holding that formation while they're locomoting towards their goal. So my work that I'm going to present today with my colleagues is more focused on this side on VFX formations. So there's still a little bit of reality, but it's more nudging towards that side. Okay, so prior work in this area is pretty rich. So you can see kind of very early on in 1987, this is not the original rendering from 1987, but this is the Boyd's algorithm, which is basically focused on flocking and kind of simulating like these kind of animal behaviors. And here on the right, I put another example of a mesh-based method where basically the group is kind of like abstracted as a mesh. So basically the user kind of just deforms the mesh, and that's how the group will kind of move when it's going to its goal. More kind of later and recently, we have state-of-the-art work from these 2 groups, Karamuzov and Brendel from INRIA in France. So these works use velocity-based approaches, which are kind of considered state-of-the-art for simulating group motion. Well, you can see the results are pretty good, but there are some deficiencies, some limitations, and I'm going to mention them kind of briefly. So the limitations are very hard to define just with velocity connections, these kind of relationships or how the group dynamics should be like. And it's very hard to support irregular formation shapes. So say you want a formation like a fractal or an arrow, it's kind of, you need like a manual definition of all of that and all those links and how strong the link will be and so on. And it's also difficult to control and implement. Like in our group, we spent a couple of months and it still didn't really work well to implement this kind of work. So we thought that we could do a better job here, kind of simplifying the problem. So again, the objectives of this work is to support large formations, kind of irregular group shapes. We want it to be interactive to real runtimes and want it to be generalizable. So we don't want it all just to work on a specific scenario, but on kind of different scenarios. So zooming out, what is the problem? What are we actually doing? So we have this is our kind of problem domain. We have agents. And like an agent can like decide to go here. So that's one navigation decision, but probably this is a better decision, right? Because that's going away from that obstacle. So all we're trying to do is kind of find these decisions that make sense. So the typical way to do this is using these force or velocity-based methods, which is kind of just extensions of Newton's second law, like F equals ma. So we're not going to do that though. We're going to use a alternative constraints-based approach. So what we're going to do is we're going to use this work from 2017 that won the base paper award in the Motion and Games conference, which is sister conference of this conference. I'm going to show you a demo of that work. So in that work, the authors kind of use constraints, geometric constraints on the positions of the agents to simulate these group dynamics. So here's a short demo of what happens there. I'm going to explain it in a bit more detail so you have a bit more kind of background. So in a traditional physics simulation, we have some sort of forces. And from these forces, we can extract acceleration, and then from acceleration, velocity, and from that, the position. Okay, so that's the basic kind of traditional kind of framework. In our framework, we don't have forces, but we do have constraints. So we have constraints on the positions of the agents. So what we want to do is kind of satisfy these constraints. So if a constraint is equal to 0, that means the constraint is satisfied. If it's you can also define like one-sided constraints. So if it's like larger or equal to 0, then it's satisfied. We don't have to do anything. And all these constraints are scalar functions. Okay, so they're all just a number. The resulting of all of these are just a number. How do we satisfy constraints? Like what do we do? So basically, we are going to find some sort of positional correction, as you can see here, that will satisfy this constraint. So because everything is geometry based. So as you can see here, like this is the unknown. What is the correction that will satisfy the constraint? I didn't say yet that this correction is actually, we actually do know how to do this because it depends on the gradient. Like any mathematical function, if you want to satisfy it, if you want to minimize it, you kind of move towards the gradient. So that's what we're going to do. So the tricky question is how to move in that direction. So to do that, we need to find this kind of unknown scalar. So the unknown scalar basically controls the magnitude that we move towards that correction to satisfy the constraint. So I'm going to talk about this in a second, but I'm going to give you a bit more background on like these constraints in general. So imagine we have a couple of constraints. For example, we have an agent that maybe wants to move here, but there's a collision somewhere else. Then what we do is we just average the corrections, like here. Okay, so if this guy has a correction over there and also over there, he was a stay put. Okay, so it's a very simple framework, but it works really well. So I'm going to talk about all our constraints and how we solve them, but I'm going to kind of zoom out into these two different areas, which are agent motion and group control. So agent motion is basically how do we control the individual motions of the agents with constraints, and group control is how do we control the actual group formations with these constraints. So these are two kind of different problems. We're going to start over here. So to begin with, again, what is our problem setting? So we have our agents, but instead of like looking at all the kinematics, dynamics, limbs, and so on, we just kind of are going to do a simplification first of all and approximate it with these disks. Okay. And now our first problem arrives, which is basically imagine you have these agents that may collide at some point and overlap. So we need to solve this. So this is not an ideal state, of course. So to solve this, we're going to use this single constraint. So what happens here? So this constraint basically means that each agent is a disk with a certain radii, and we want this constraint to be kind of satisfied for all the pairs of agents throughout the simulation. Okay, so I'm talking about the stiffness here because we want it to be fully satisfied because there's no partial overlaps. We just want the overlap not to happen at all. And on the right-hand side, we have this long-range collision avoidance, which means that agents should avoid colliding even before the collision will happen. So the stiffness there is time-dependent. If you want more details, I'm going to refer you to the 2017 paper, just for the sake of time. But here's a quick demo of what that means. So the blue agents are kind of using the short-range avoidance mechanism, and the red agents are using that long-range mechanism. You can see the behavior is completely kind of almost similar, just ahead kind of in time. Okay, so that's our basic agent control. We didn't do anything new. We are just kind of reusing that framework from 2017. Now, this is the new thing. So how do we do group control? So group control, so again, there's two sub-problems here. So first of all, we want to maintain this formation shape somehow. That's one problem. Another problem is we want to kind of match agents to their ideal position in the formation. So because agents, for example, that agent in the yellow here, there's no need for him to just stay in that single position. He could be reassigned to any other formation kind of position. So I'm going to explain this more later if this is not clear. We're going to start in this kind of sub-problem first. So I apologize for the math. This may seem heavy, but I'm going to explain it kind of slowly. So what is happening here is we have our group here on the left in this diagram, and the agents in red, they have moved. And now they are kind of to the right of that arrow. And we want to find what formation should they be in so it matches the original kind of initial configuration. So basically the problem is to find these things. So to find what is the rotation of the formation and what is the translation vectors that lead the groups to that ideal positions in the formation. Okay, so these are our nodes. We need to solve this somehow. So luckily, this is a problem that a lot of people have worked on in physics and graphics deformation for meshes for many, many years. So we're going to try to reuse some of these solutions. So we're going to solve this with shape matching. So a quick overview of shape matching. So what happens in this method is like you simulate the mesh as a system of particles by placing particles at the mesh vertices, like you see here. And you save the initial positions of the particles as the rest configuration of the object. So that's basically the dashed lines over there, to which you want this object to return to eventually. So in the diagram, you can see that that's your ideal group position. And here's a demo from the original SIGGRAPH presentation. So during the simulation, what happens is the particles move independently in response to users' kind of interactions, forces, gravity, and so on, and collision, and so on. So the job is kind of to find this optimal orientation, rotation, and the translation vector. And this is basically a optimization problem that you need to minimize the sum of the squared distances between the particles and their match positions. So I'm not going to dwell too deep in because we actually we're kind of like just following this work. And if you want more details, you can just review our paper. But this is what we do. We're just going to find this optimal rotation and transition using this kind of a method from 2005. So a couple more details, right? That's not, of course, that's not all what we do. So all our formations are basically one cluster. So there's other shape matching papers where they have multiple clusters and multiple kind of deforming shapes. So everything is just one cluster for us in shape matching kind of literature. And we also we can support multiple deformations. We have more clusters like you see in this video. This is also from the original 2005 work. So the more clusters you add, the more kind of deformable kind of shapes or formations you get. Here's a quick demo of what this actually entails or means. So circle again versus rectangular. So again, only one cluster for each of these shapes. I'm noticing a lag. I apologize. That's not up to my control. That's like something with the system. It's like real time on my screen. I promise you. Okay, so that's problem number one. Problem number two here is actually assigning the agents to the right position in the formation. Okay, so what's happening here is we have our, if you look at this diagram kind of closely, there's like the yellow agent over there on the bottom, kind of close to the front line. And during a simulation, dynamics happen, things happen, and that formation is disturbed, as you can see here. So that agent has been pushed back kind of very, very much. So without reassignment, he's going to keep thinking that he has to go there. He has to belong to that specific position in the formation. But with reassignment, we're basically reassigning the agent to a different position that more aligns with the current rest configuration of whatever is the optimal solution for that formation shape. So that's with C here. I'm going to talk about this in a bit more detail. So again, to solve this problem, we need to kind of formalize it. So the formalism here is a sort of a matching problem. So to remind you, maybe you saw this in undergrad. So a matching problem is basically you have nodes and you have to kind of match the nodes from X to Y. Okay, so that's your matching problem. And what we want to do, that we want to match it while we're kind of minimizing this thing over here, which basically is the distance between where the agents are right now and where their group positions should be. So this is very nice in theory, but like actually not in theory. This is actually NP complete. So as everything in NP complete, you like see that NP complete is like, okay, maybe I should do something else. But actually, luckily, in 2D, there's a very nice polynomial time algorithm that can solve this problem for us kind of quickly. And this is courtesy of SciPy. So you can just use SciPy to solve this problem. So let me show you an example of what this means for us. So this is without reassignment. First of all, you can see the effects of kind of people kind of moving without that matching active. So you can see it's actually pretty nice, but still there's like some sort of like kind of conflicts, I would say. And this is with reassignment on. It's a lot faster, smoother. No, not much of that like internal conflicts in the formation shape. Okay, so I'm gonna show you some results. I'm gonna do some discussion, and like we're gonna finish the talk after that. So here are some initial results about column shape groups. So this is like the simplest thing I can think of. So here we have kind of agents in kind of column shape style formations, kind of locomoting to the other side. Again, there's different kind of showing you different kind of responses, so they can either go through or go aside. This is kind of typical thing you would see in like a crowd simulation benchmark. You just want to see how your algorithm kind of interacts in different kind of situations. So even if it's very dense, they still are able to kind of move, nudge about, and kind of move to other side. And you can also make it a bit more kind of that. I'm going to also show you what happens when they're very dense, and you're going to see the response. So we are very dense, so we saw about kind of sparse formation. If we make them very dense, you get this kind of reaction. So it's kind of like they're almost having to stay in the formation. They have to kind of pivot around each other, kind of as a group, kind of like what you would expect if you were like watching like that marching parade from China or something like that. You would expect something like that. And we can also support this kind of different kind of interactions kind of between kind of, if you just is a top view of the formations moving around. We can also have, this is like a common example in like what happens if you just send people to the center from different corners. So here we have triangular groups kind of moving around, and they're kind of, there's like some sort of vortex forming, which is what you see even in singular agent kind of cases, which is good because that's a phenomena crowd researchers like to see. Here's another example. We have like this kind of free case kind of crossing example where we have multiple formations kind of interacting, and they're still kind of using that constraint to maintain the shape, and it's kind of smooth, and that's kind of good because that's what expected behavior is. Okay, here's a funny example. So here we have like a fractal, two kind of fractals. So we support different kind of formation shapes, whatever you want. Smiley face fractals, I don't know, letters. This is kind of complex, so I like this example because it kind of shows like we can do kind of whatever you want in terms of the formation shape. And this is all like real time. So the actual, I'm going to talk about this in a second, but the speed of running it is this kind of compute of this group constraint is like almost 5% of the entire compute. There's a lot more happening that needs more compute. I'm going to talk about in a second. That's not related to these group constraints. Okay, so a couple of formulas and implementation. So basically, in our framework, every constraint has a stiffness or a strength. So you can see that basically as a measure of how fast he wants to resolve that constraint. So for example, if you want to avoid collisions, you want to avoid them now, not like later. So that's a very high stiffness. If it's like a long range collision, so that you tweak to be by see the time or some like lower fitness. So you don't have to really observe it immediately. And all the constraints are linearized. So this is just like you can just solve it with very easily on any framework. And we of course use a GPU to solve this kind of in parallel in real time. And I actually use this computer. It's real time. This computer, it's like a MacBook M1. So it's not like crazy computer. It's not CUDA. I'm sorry, NVIDIA people. So just so, and if we look at the performance, it's kind of linear in the time number of agents, and you would expect that because what we actually do behind the scenes is you would think that the pairwise agents is and squared problem, but no, it's like linear because we have a nice spatial hashing, which is algorithm which is like fast on the GPU. So it's basically a radix sort, but it's very fast. And if we didn't have a GPU, it will be maybe fast for like hundreds of agents, but not more, hundreds of agents. It's real time only because of the GPU. And to get all of this working, we use this framework called Tai Chi Lang, which is a SIGGRAPH paper from 2019. Here's a quick rundown of the paper. This is like something you can all download. It's on GitHub. I'm not like, I don't know the author. I just said hi to him once, but this is very nice if you have like a Windows machine and a Mac machine and you want things to run. You don't want to code that in Metal. You just use this framework, and it just all that writing for you. It's nice if you're a researcher. Anyway, some more points. So our framework kind of easily supports more constraints. It's and a physics constraint because you can everything that you can find with physical constraints like fluids, sand, as many people did already in Unity or like in Houdini or Blender. Then you can add them to this framework. So for example, large crowds behave kind of like a fluid, so that will be a cohesion constraint. And if even denser crowds, like for example, very large stadium, like dense stadiums, you can have a friction constraint to kind of slow down the agents as they're interacting. So our method has several limitations. We're not, I'm not saying we're perfect, but first of all, right now our formation is orientation agnostic. So for example, imagine the group is going towards this kind of opening. So it right now, we didn't add support. We kind of didn't have time, but it kind of doesn't know it has to pivot to enter that area. So here's another example of what that means. So here we have like our group going, and you can see the formation is kind of, there's an orientation, right? But it's not, you're not like kind of maintaining that orientation throughout this group simulation. So this is one orientation, for example, and as the group continues to move, there's going to be a different orientation. So right now we don't have a constraint to maintain that orientation, not because we can't, but just ran out of time, but that could be like subject to future work. And you can see that stopping over there, and that's going to have a different orientation over here like that. So we're not maintaining right now the orientations of the groups. And yeah, I also mentioned the environment versus the formation. So if you have a like static walls or some sort of like kind of obstacles that are not moving, we are not right now. We're not taking that into account in the formation. Though we did try, and we have solutions for that. We just not in this paper. So right now, I'm just going to summarize my talk. So we showed that we kind of saw a constraint-based framework for group and multi-agent crowd simulation. It's fast by combining position-based dynamics and a GPU implementation. It's an alternative to velocity or force-based techniques. And it's easily implementable in VFX pipelines, which already use position-based dynamics like Unity or Houdini or Blender or whatever. And I want to thank all my collaborators and colleagues. And if you have any questions, I'm here. Thank you.
Amazing. Well done. And I really love the all of the visualizations. Does anyone have any questions? Okay, I'll start. Okay, no, you go ahead. Laurent? Yeah.
Thanks. You said you were using a Jacobi solver for your constraint. I assume your stiffness constraints are symmetric between the two agents.
Correct. Yep.
So would it be possible to use a conjugate gradient instead?
Well, yes. So we didn't try that, but yes, there's work on how to use PBD with conjugate gradients. There's a paper, a SIGGRAPH paper, I think by Yuming Wang from Ohio State. We didn't do that, but yes, that's subject to future work.
All right, thank you.
Yeah.
Any more questions? Okay, go ahead.
Thanks for the talk. I have a question about whether you have considered the application of your method to a different field like swarms of drones. And
Right. So we do have a 3D 3D kind of multi-agent simulation paper, which is kind of drones but not swarms. If you want to go to the swarms way, yes, we can do it with swarms. The only problem is that we need to think how to sell it to graphics people. So because but yeah, so that will be more like a robotics paper. Yeah.
Any more questions? Okay, so I'll do mine. So there's one thing that's really obvious, well, from all crowd dynamic papers, but this one is also following that making a crowd controller is one of the least intuitive things for artists, right? You have all the simulation running,
Right.
and then you as an artist can't really navigate them because they'll have to realign themselves. How do you see this progressing now that you have like the shape solver?
Well, I think there was work in I3D, I think maybe 2 or 3 years ago, and there was work in motion games about kind of more intuitive user interfaces for sketching crowd control. That was led by professors from Purdue, I think Gedalia. So that may help a little bit with that. But with the shapes, I think if you can easily sketch. So basically, we in our initial experiments, we just sketched the shape and like opened it in this simulator, and then we just ran with it. So we just didn't we didn't think about how to productionize it. So we're just like using one kind of script to kind of sketch the shape or like draw the shape, and then you can just open it. So it's a bridge very easy to cross, but we didn't do it because we're not like selling this as a product or anything. So, yeah.
Thanks so much.
Yeah, thank you.
So okay, up next, we have a paper which is one of my personal favorite topics. Like every year you have like at SIGGRAPH or at GDC a paper about sand simulation. And until recent years, they weren't really able to do like any kind of like interparticle dynamics, or like very limited in size and couldn't stack and so on. And this year we have the sand paper that actually can do that. And to present it, we have Brennan Taylor who was a PhD student at the Department of CS Engineering at Texas A&M.
Awesome. All right. Hi. So like you said, my name is Brennan Taylor. I'm from Texas A&M University. And so this is some work I did with my advisor, John Kaiser back there. So just as a bit of an introduction, I want to give a little background on sand simulation, in particular, the area that we're focused on. And so there's a lot of different disciplines that are going to desire to capture realistic sand behavior, not at the level of individual grains of sand, for instance, like a very small sandbox. But no, this is more kind of focused on large scale terrain, or potentially, sand ripple interaction, things like that. So one domain that comes to mind is geoscience. And so in that area, a lot of what they desire to do is predict long-term sand dune propagation. So the idea is, okay, what is the state of a current desert? What are the major kind of wind phenomena that are present in that area, and how might they interact with civilizations, like cities and things like that. As well as our climate is changing, this is going to be very important to be able to predict how those changes might affect things. Film is a different area that comes to mind. So they want to simulate realistic desert environments. timely. We had Dune released last year, and the trailer for the second one just dropped, so that's very interesting. So for this, those industries are going to want to minimize the amount of artist time and in general render time. And so the idea is maybe we can have an artist come in and simulate using a physical model like ours, the evolution of terrain, and then pick the parts that look nice and things like that. Lastly, games, I think, would be a good domain for this. And so we can actually have interaction with the player. So this is less on the scale of, you know, a 1 kilometer by 1 kilometer environment. You'd have more sand ripple behavior. So we'll see that in a second. So in general, dune types manifest on a lot of different factors. So they're transported by wind. And so this is called an Aeolian process, or wind transport. So the wind direction that's present in the environment, as well as the amount of speed present, is going to change the amount and of sand transported in the shape. Sand availability is going to be important. We'll see that later during our verification that we chose to do. And then terrain gradient is actually very important. So you can imagine with a very steep cliff, the interaction of sand dunes with that cliff is going to be a little bit different than what you might expect. And so that's going to be important for something we call an echo dune. I'll show that in a second as well. And then lastly, vegetation can have some impact, but we don't focus on it too much. It's more for parity with the previous work. So I actually, when I was doing this research, was surprised to see that a game had sand ripples. And so in this scene in God of War, you can actually see all of these sand ripples that are present in the scene. However, on closer inspection, it looks like all they're doing is actually having a height map that's being translated. And so there's no actual physical process happening in real time. And so using a technique like the one we're presenting, you could actually have these sand ripples evolving in a way where they interact with the rock, they interact with the pillar, they interact with these obstacles, and have a realistic kind of feedback from the player. So some different types of dunes that you're going to see. So one dune structure is called a Barken dune. So this is caused in a uniform wind direction environment with lower sand availability. So if you have that wind projecting on the left, you're going to see a real world image. And so we have the wind moving in that uniform direction. And you get this kind of crescent shape where you have these long horns which extend in the direction upwind or downwind. And so this is a production of the Barken wind using our method. Transverse dunes are probably the ones that come to mind when I say, hey, picture sand dunes. So these are long kind of parallel waveforms that form inside of a desert environment. But if you've been to the beach and you see those sand ripples, it's the exact same kind of dune playing out in a very much smaller scale. And so here's also a visualization of our method. Lastly, you can have in more complex wind regimes, different formations of dunes. So you can imagine with like a star dune, this is the case where you have multiple converging primary wind directions. So you have a highly changing. So imagine if the wind were to change direction throughout the day, the sand would blow back and forth, and finally it would pile up in the center. And so you get some avalanching behavior where basically that sand's not going to, it piles up to a certain limit and then it's going to cascade down due to gravity. So that's going to be very important as well. Lastly, one type of dune that we identified in particular that we wanted to work on was echo dunes. And so this is basically caused by sand dunes propagating into a high terrain differential, like a cliff or something like this. And the wind that actually comes in, interacts with that cliff is going to have a reverse eddy current form. And it is going to push sand back away from the cliff face itself. And it's going to cause an echo shape of the cliff itself in a sand dune. So the sand dune is going to form kind of the same shape of that dune. Or that cliff, sorry. So all of this is based on a prior work. We identified this work called Desert Shape Simulation. So this was from Pacific Graphics in 2019. However, this was a CPU-based kind of stochastic event-driven framework for modeling sand. It captured some of these types of dunes. And so the idea with this previous method was drive everything with a high level wind field. So you could have a 1 kilometer by 1 kilometer grid with some certain resolution, and then you would provide a overarching wind vector for that scene. And then with that, you're able to generate a wind field by projecting that, that wind vector down onto the terrain. It warps a little bit. I'll go through this a little bit more. We're going to generate wind shadows. I'll explain what that means. We transport the sand. So sand is transported in two main ways. So there's saltation, where sand is lifted by the wind and propagated forward, and then it's deposited, or reptation, where that sand that's deposited strikes the sand bed itself of resting sand and can cause some recursive bouncing. And so all of this is handled in an event-driven manner. Okay, so it's all resolved one at a time. I'll talk about that in limitations. And then lastly, avalanching sand is required. So if you have sand piling up, which it's going to do in a dynamic environment, at some point you're going to have to resolve the cascading of this because there is a maximum angle of repose for sand. And once a block of sand, for instance, has too much height compared to a neighbor, it is going to cascade in that direction. So with the wind vector, you essentially just project this down to the terrain. You change the speed of that wind a little bit by the terrain height. And so higher terrain is actually going to have higher wind speeds. And so that actually leads to an increase in sand being picked up and deposited over the side of the dune. That's kind of what causes that shape. And then wind shadow is going to capture the effect of being downwind from a dune. Wind is going to slow down and you're going to have a much lower chance of that sand lifting and actually more likely to be deposited in that location. And so here's a visualization of if you have that dune downwind, that P position is more likely to or less likely to be lifted. For transport, the way that this is set up, essentially you have multiple grids of height fields stacked on top of each other. However, they're discretized. So these aren't floating point height fields. What we do is we actually have an integer count per cell. That's going to be important for implementation on the GPU. But essentially they're discrete volume blocks of sand stacked on top of each other. And during the sand transport step, we lift a certain amount of these blocks, propagate them forward, and then resolve and things like that. And then avalanching is handled in the same way. So major limitations of this previous work were as followed. One, it was tied to the CPU. So they had this event-driven kind of stochastic view on it. So what they would do is they would move a single block of sand, they would project it forward, and they would resolve everything. So they would do reptation events that would trigger out, and they would queue those up in an event, and then they would resolve those. They would queue up any avalanching events, and they would resolve those as well. And that is even a recursive process. You can imagine that propagating over an amount of distance. And so would that need to be reformulated for the GPU? Okay. There's also no robust handling of echo dunes. And so in those environments, anytime you would have steeper cliffs or terrain, the dunes would just climb right over it. You don't have any of that echo dune forming in front of these cliff faces. And that's because the wind model is just not complex enough to capture those reverse eddy currents. So we wanted to explicitly handle that. And lastly, there's no good validation method so far. So the previous method, essentially they said, here are some dune shapes that appear in the real world. We're able to produce some of those dune shapes. And so we wanted to try to begin a process of verifying our method a little bit better. So in general, our research goals were following. Bring sand dune simulation to real time. We can actually use this in something like a video game. Maybe that God of War Ragnarok could have used this method. We want to introduce echo dune support. And so we want to correctly model dune interaction with cliffs. And then we want to validate the model against a ground truth. And so I'll talk about the model we selected for ground truth a little bit, but it comes from the geoscience domain, actually not the computer science domain. So in general, for the real-time GPU simulation, this is the following model. So on the left, what you can see is anything that's like a three-dimensional box, that's going to be a sand block map. So this is the discretized grid of sand blocks stacked on top of each other. So we start with our previous step. We can optionally add sand. So any of the gray passes are going to be just pieces of the simulation. And then we have this combined sand result, and we throw in our wind vector, begin doing some of the simulation. The center part is solely for echo dunes. So we introduced this. So we introduced two new masks. You have an obstacle map, so you can actually bake obstacles down, and these are stacked on top of a underlying bedrock layer. So you have a bedrock layer, which is the main form of the terrain. You have sand on top of that, and then you have obstacles which are embedded inside of that bedrock that we want to interact with the sand. And then we introduce a concept called sticky cells. So sticky cells are what are going to be used for actually causing the formation of these echo dunes. So just keep that in the back of your mind, and I'll be talking about it in a couple of slides. Lastly, we introduce a little bit of vegetation and then have our overall transport steps. And then we transport the sand, and then avalanching is actually handled not in an event-driven manner anymore. It is an iterative manner. So I'll talk about why that was necessary here in a slide. And then lastly, we can bake this out and composite it for height map for real-time rendering. So all of this is on the GPU. So the majority of the passes were straightforward to parallelize. And so one of the key intuitions was you don't have to do this in a kind of single event driven manner. You don't have to focus on a single block of sand. All of this should be able to move at once and be resolved. And so we can perform a sand transport step on every single cell. That doesn't guarantee that sand is going to move from a cell. It's going to depend on the probability of sand, the amount of sand, wind speed, things like that. But it can happen. However, you could have multiple blocks converging to the same location. And so this is why we actually went with a discretized version of sand blocks stacked on top of each other, because we needed to resolve these colliding sand deposition events in a predictable way. And so we handle that with atomic rights. Lastly, another thing that we ran into was a number of these passes are going to feed into each other, but it wasn't very efficient to write to one copy and then copy it over and then keep basically modifying the exact same sand block grid. And so we handled that in a double buffered approach. And so while the sand transport step might read from buffer 1 and write to buffer 2, we're going to flip those two buffers, and then the avalanching iteration 1 is going to read from the opposite, and then can you continue on? We'll just keep flipping these buffers. And that proved to be very efficient for an implementation. So avalanching did require rethinking a little bit. Previously, the ground truth way of handling, or what was in the previous method, the ground truth, was resolving a single block at a time. So you would have, for instance, this block of sand, we might move toward a neighboring cell, and then that could trigger moving to its neighbor, and so on and so forth, and you'd resolve all those in kind of a predictable manner. However, that is very bad for the GPU. It did not lead to any, there was no way we were going to implement that. And so what we've done is we've reformulated as an iterative process. So instead, we simply move a small percentage of the center sand that's going to be avalanching to its neighboring cells, and all different grid cells are able to avalanche sand to their neighbors. Okay, and so this is done in a small iteration. And so there's a trade-off between the amount of iterations required for stability and the suppression of dune formation. Basically, if you have too many passes, it can suppress creation of dunes a little bit. If you don't have enough, you're going to have unresolved avalanching. So things are going to stack up unnaturally high. But there's kind of a sweet spot between 25 and 100 where you can move just a little bit of sand per iteration, and it seems to converge out fairly nicely. And this led to an efficient compute shader implementation. And so the resolution of that would look like this. So in general, the performance of this was exactly what we wanted. And so across the board, it was much better than that CPU-based approach. It was very efficient, and it increased as the grid cell resolution increased as well. And so overall, not only did our speed up compared to the CPU increase, we found that we were able to achieve real-time rates, fully interactive, with a 0.5 meter resolution for a 1 kilometer square environment. And so you could imagine if an artist was wanting to interact with this large scale environment and see the propagation and kind of generate an environment without having to sculpt it, they could do so. All right, so moving on, I'm also going to talk about echo dunes now. So the explicit support for this. So we identified a work, and this work was done in geoscience. And essentially the focus of this work was, let's use a wind tunnel to simulate the creation of these echo dunes, okay? So in the real world, it can be pretty difficult to capture these explicit methods, or the creation of these dunes, because it happens over such a long period of time. So what they do is for desert sand, it's fairly large. What they'll do in these wind tunnel experiments is they'll use a very fine-grained sand, and they'll try to replicate the exact same kind of scale for the desert sand size. And so what they found was there is a consistent parameterization based on that height differential for the cliff itself compared to the neighboring terrain for how far away these echo dunes are going to form around that cliff face. So based on that parameterization, we created the following model. So what we do is we first identify cliff cells. So you can see here on the right, we look at all of the cells at once, and this is per cell. We look for those that have a neighbor with the height differential over a certain threshold. We mark them as cliff cells. We then continue back upwind. This is all against the wind direction, identifying echo cells. So right here, you see a visualization in gray of single echo cells. But if that height differential was to increase, the number of echo cells would actually increase in scale a little bit higher as well. So these echo cells, we enforce two things. We disallow deposition, and if any sand actually happens to avalanche or become deposited in those locations, we quickly erode it away. And so that erosion, it models the effect of the eddy currents pushing that sand very rapidly out of that center location. Lastly, we mark upwind again a number of sticky cells. Okay, so a sticky cell essentially is us painting a function of probability. So the idea here is, again, dependent on that cliff height, we have a large spread of probability. That furthest from the echo cells is going to be a lower probability, and that most close to the echo cells is going to be higher. And during sand transport, we are going to, based on this probability, have a much higher chance of deposition at the locations with a higher probability, and vice versa. Sand is much less likely to be picked up. So this plugs directly into the model from Pacific Graphics. So you can see here is a square cliff where we have this object. I apologize for the programmer art, but you have the very hard kind of square shape of this echo dune forming. And then for a little bit more interesting environment, we can have a rounded cliff as well. And you see that as the wind vector, which is moving directly into the object itself, begins not aligning with the normal of the surface, you get that sand dune begins to wrap into the object and then travel perpendicular to the normal of the surface. So this is all interactive. And so here I show a couple of frames from removal and placement of the object, but I'd rather just show you a video of us interacting with it. So here we have a steady state. In this case, the wind vector is actually coming in at an off angle. Again, same issues as everyone. It's a little bit more choppy than my screen. But we have a steady state reached with an echo dune, and we can remove that obstacle, and the sand begins to propagate and fill in that area. And then if we were to retoggle that obstacle, essentially we're baking it back into the sand map. You have that echo dune quickly forms, and then the sand is actually going to travel away from that far side of the dune. All right, so lastly, the thing that we wanted to do was validate our model. So what first came to mind was, okay, let's look at real world data and let's see if we can exactly capture that. Well, unfortunately, there is a large lack of real world ground truth measurements. So the reason for this is what you have to do is go out to a desert, set up a large spanning array of very expensive equipment, try to register over a significant amount of time the amount of sand moving, essentially the flux. It's expensive, it's noisy, it's just not there. So instead what we did is we looked to the geoscience domain. So there's a very well-cited paper. It's fairly computationally efficient and implemented on the GPU, but nowhere near real time. And this is a cellular autonoma-based approach. And so they essentially allow they have a three-dimensional grid of cells, and they can allow any two neighbors to flip from like source to sand or sand to wind, things like this. They also simulate a lattice gas model for full 3D wind effects. So this is a highly detailed model. Again, not real time. But there was an additional study performed later using this model, this cellular autonoma one, to explore dune behavior in a number of regimes. Okay, so this is where we start exploring the behavior of this rescale method with different sand availability, as well as a different bidirectional wind regime. And so here on the left, you see an amount of sand availability. So this is a percentage of sand covering the entire kind of environment. So we range anywhere from 7 to 100%. And then the bidirectional wind environment means we roughly expose this primary red wind vector twice as much as the blue vector here, but then we modify the angle between them as well. So what we wanted to do was see, can our method actually reproduce the same kind of environments and treat this as a validation? So the idea is, if we can replicate the same kind of dune structures in the exact same wind conditions, we begin to start validating this. And so we did so. And we found that the majority of environments, we were able to replicate this dune structure. We found that in very low sand availability, so for instance, you start dropping off to 22 or 7%, we do fail to form kind of these long tails, which appear in the rescale study. We're not sure if this is an effect that rescale is not capturing it or our method is not. And so that's going to require a little bit further exploration. This is something called a longitudinal dune, where you have these two vectors that align very carefully. And so you have these long kind of stretching effects. And so we'll want to see if we can replicate that later. But here you can see some real-time interaction where we validate our Bark Dune scenario. So here what we're going to do is toggle on a little bit of sand. So again, bark and dunes are uniform wind direction, low sand availability. So you see that the crescent shape that's very characteristic of these bark and dunes forms very rapidly. And then also we generate transverse dunes. And so it's going to be the exact same wind environment. Again, it's a uniform wind, but much higher sand availability. So we start adding a lot more sand. Again, apologize for the choppiness. But you start to see this transverse dune shape appearing in real time. So in general, we presented a real-time GPU implementation of sand dune simulation. We were able to capture that echo dune formation for these cliff differentials and terrain differentials, which we were targeting. And then we validated our technique against a parallel but quite different computational approach in the geoscience domain. There are a lot of limitations in areas for future work. So currently, everything's tied to one simulation grid. So one thing that keeps coming keeps coming to mind for use in games, for instance, is you would have to have separate grids for different obstacle interactions, and you'd need to be able to propagate that across. And so right now, we don't have a good solution. I'll, in future work, kind of mention one that we thought of. But right now, all we do is we wrap the environment. And so any wrapping is going to allow us to tile, but that would be very noticeable and repetitive, things like that. Additionally, the wind model is extremely simple. And so one of the next directions of work is going to be viewing a full 3D simulation or some kind of layered 2D wind model. And our hope is whenever we simulate more complex wind, we won't have to explicitly add support for things like echo dunes and handle them in their own path and separate passes, because maybe the wind model will capture those more complex wind effects. So like I mentioned, improved wind would be a good area of future work. We think neural network prediction would actually be good for a couple of different passes. So the avalanching pass is one that comes to mind. It's very sensitive to the number of iterations and some different parameter settings for the simulation. And so the idea is maybe we can use something like a CNN network or UNet or something like that to predict from a fully unresolved kind of sand block state after sand transport, the fully resolved state. So we could just do that in one single pass. We also think that maybe doing the entire pipeline would be a good candidate on just see if we can actually generate maybe based on a terrain shape, or we could propagate a number of stages. And lastly, I just kind of wanted to mention one of the ideas that we had. So this is our first idea that we wanted to explore, and it didn't pan out so far. But the idea was using sand transport primitives to actually propagate the sand. So I mentioned that what we're doing is we're lifting these discrete blocks of sand and moving them. But what you have to do is actually move them forward along a wind vector and then drop them down, and you could be skipping cells in between and things like this. The way sand works is over a long period of time, it's continuous. It's a probability distribution of where that can be deposited. And so what we wanted to do was lift these blocks of sand, but then render out using the rasterizer kind of this probability distribution and actually in world space stamp this down onto the grid. Unfortunately, our implementation of this proved to be slower than the grid-based kind of compute shader approach that we already took. But we think that maybe exploring compute shader rasterization or some different approach might lead to a way to actually stitch multiple of these grids together. So with that, here's the references, and then any questions. Thank you all.
Like I see immediately that with the latest session at SIGGRAPH for advances in real time, they spent about 5 hours discussing a weather system and a water system. Having an added sand system now is going to appear in like every game in 2 years. So any questions?
Thanks.
I was kind of wondering about whether this could be applied to other situations like snow, for example, people around
Sure. Yeah. No, it would. That's a very good candidate. So the rescale, the geoscience domain, there was a little bit of recent work exploring using that geoscience framework for snow simulation. Now, one major issue that would come in trying to port that over to the stuff that we presented for sand is, and this actually would bring up wet sand as well. If you were to have a rainstorm or something like that, snow and wet sand is going to have kind of this cohesion parameterization. So all the transport in this model is probabilistic. And so it's what's the likelihood of lifting sand from this block? What's the likelihood of depositing it? And so what you could do is you could tweak those probabilities to simulate cohesion a little bit. And so you could say, hey, if this is wet sand or it's snow, it could be very less likely to be lifted or more likely to be transported or deposited or something like that. You would have less bouncing and things. But yes, I think that would be a good candidate.
Yeah, thank you. Really interesting thing. I wanted to ask, how do you handle the sand on boundaries of this grid? So basically, if it possible that all sand go away from this grid, and how do you handle?
Sure, yeah. So there are two ways to handle that. So one is you could just have sand blowing in from off screen and it could fall off and you could just erode it away quickly or something. But the way we handled it, at least in these environments, was we just wrapped it around. So that is one of the open problems and why we kind of explored that, that rasterization-based approach, because that would be in world space, which we would then render down to these grids. But finding a way to have neighboring grids and resolve essentially the transport across as well as avalanching across those boundaries is open and very difficult. Good question.
Yeah, I have a couple of questions. The first one is really trivial. Just, could you give us an idea of what resolution of grid you were using in those demos you made?
Yeah, that was a 1024 by 1024.
Oh, thank you. And the second question about your avalanche problem, about propagating. Have you looked into like something like going backwards instead of going forward? I'm thinking of like, a method of characteristics approach, basically, of actually backtracking so you could actually know which amount of sand you're bringing into each step.
I'm not sure if we actually can, that would be very interesting, yeah, because the idea would be, okay, so what is the probability of an amount of sand being deposited at this location? One of the nice things about taking it, lifting it, and propagating it forward is that's fairly trivial to resolve because you move it and can resolve it. Moving backwards, I don't know. The issue there would be the likelihood of lifting sand is based on the presence of sand at that location. So if there's bedrock exposed, for instance, you're not going to lift any sand. There's nothing there. And so if you were to do things backward in time, you could have, it would be a little bit difficult. I'm not sure. I think that's an interesting idea.
I just wanted to, I was just wondering if you had looked into that.
Yeah, no, I'm going to think about that. Thank you.
More questions? I have one. So
Sure.
Can you talk a little bit about the quality, like how you mentioned that basically the quality of the motion vectors is incredibly low, and you're earth moving. You're literally earth moving, not just in mathematical sense. Is there a way you think of it a way you could iteratively improve the vector map just based, like the motion vector map, just based on the simulation itself without having to add more dynamics?
It's possible. So one idea that came to mind would be essentially trying to do the edits, not in like the sticky cell sense, but actually modifying the wind map itself. So it'd be identifying the locations where these eddy currents would form and actually stamping wind down facing away from the cliff surface. So forcing that. In my implementation of that, we found it to be very unstable, and that's going to be resolution dependent. And so if you have a 1 meter by 1 meter square or even a larger one single wind vector pushing back is going to cause a lot of oscillation in that boundary, and it's not going to essentially form that echo dune. Things are going to push up against the cliff, and so that's one thing we ran into.
Right, and there's a paper by NVIDIA from like a while ago on how to implement waterworks and the trick of having a water cage basically for where you have turbulence. Like you can make it local, because I see in your paper you don't have basically you're not maintaining a constant amount of sand in the simulation, right?
Yeah.
Same relaxation goes there. You can do that. So thanks so much.
Yeah, thank you.
Yeah. So the next paper is differentiable curl noise. Boundary respecting procedural incompressible flows without discontinuities. and it's presented by Christopher Batty's group in Waterloo by Xinwen Ding. Can we roll the video?
Welcome to this presentation, Differentiable Coronoids, Boundary Respecting Procedure Incompressible Flows Without Discontinuities. My name is Xinwen Ding, an undergrad student at the University of Waterloo. This is a joint work with Christopher Batty. In this presentation, I'll introduce differentiable coronoids, a continuously differentiable procedure method to animate strictly incompressible fluid flows in 2 dimensions. So after reading this sentence, you may ask, why are we focusing on a procedure method? This is because, unlike a PDE-based fluid simulator that will only output the whole simulated solution as the final step, a procedure method gives its user greater controllability, which allows users to directly edit the flow. And why are we interested in developing a differentiable scheme? This is because, by the design of the original coronoids method, a differentiable scheme will ensure a smooth and natural velocity field. And under such field, we can generate mathematically and physically plausible procedure animations where fluids flowing past arbitrary static simple polygonal objects. So before we move any further, let me introduce you the problem setup of coronoids, as well as some notations that will be consistently used throughout this presentation. So first, let us define a bounded domain of interest D and put a query point X inside this domain. Next, we put n objects in the middle of our domain. We name them O1, O2, all the way to On. Notice that in this work, we're interested in simple polygonal objects. For simple polygonal objects, we let dk star to be the distance from the query point X to the case edge of the polygonal object. Let the I of X to be the minimum signed Euclidean distance from the query point X to the ith object. Notice that for a polygon, we write di of X as the minimum distance from the query point to all its edges. Next, we let d of X to be the minimum signed Euclidean distance from the query point X to any objects placed in the domain. By definition, we can write d of X to be the minimum distance from the query point X to all objects. In our example on the right, we write d of X to be d3, since we can see d3 is the smallest distance. Here are some relevant literatures of coronoids. The one on the left is the original coronoids designed by Brisson et al. In 2007. The paper on the right is a recent modification proposed by Chang et al. In 2022. In both papers, we are given a continuously differentiable user-defined potential psi. We let V to be the velocity field. The coronoids method was built upon the observation that if we define the velocity field V as the curl of the user-defined potential, then the divergence of the velocity field is 0. This recovers the key feature of any strictly incompressible flow. Then we place solid objects in the middle of the flow, and we modulate the user-defined potential psi in the regions near the obstacles, such that we make the boundaries of the object as an isocontour of the modified potential. Therefore, the fluid does not flow into or out of the objects, and we obtain a modified background potential psi prime. In the plot below, we set the boundary of the circle to be an isocontour of our modified potential psi prime. Next, let us look at how the existing methods modify the user-defined potential psi. Let d naught be the influence radius, which is a predefined constant. By saying influence radius, what we really mean is that the coronoid scheme will modify the user-defined potential if the distance from the query point to the closest object is less than d naught. Otherwise, the modification scheme will do nothing to the user-defined potential. The user-defined potential psi will be modified according to the following rules. The first row shows the original coronoids proposed by Brisson et al. In 2007. The second and third rows are the multiplicative and additive ramping strategy proposed by Chang et al. Recently in 2022. Below, we explicitly write down the definition of functions, such as alpha x and the ramping function. Notice that the psi g function appeared in Chang's design is the target boundary potential, that is, the target isocontour value on the boundary of the object. And in practice, psi g is the potential evaluated at the center of the closest object to the query point x. Finally, the function Cp of x in Chang's design is the closest point projection from the query point x to the boundary of the objects. However, we found that all the existing designs are not differentiable. Let us consider a simple rightward flow. We make the following isocontour plots of the modulated potential psi prime of x. We see from the plots that all these constructions have strong artifacts, such as the tangential flows surrounding the objects in the original Coronoids design, and the clear discontinuities from both of Chang's design, even if we place circular objects that have smooth boundaries. After a careful investigation, here we make a quick summary of the 5 problems we found that prevent the existing method to be at least continuously differentiable. The first 2 problems directly comes from the main function in the definition of distance functions, di of x and d of x. The third problem comes from the function psi g of x, since it depends on the locations of objects. Recall that psi g of x is the user-defined potential function evaluated at the center of the closest object to the query point x. And we cannot expect the centers to be continuous, since the closest object will change. For the first problem, we found that the constant influence radius d0 restrains the relative locations of the objects. As shown in the isocontour plot below, a clear discontinuity occurs between the 2 circles that are very close to each other below. Yet, we found no issue between the pink circle above and the 2 circles below, since the pink circle is located far away from the rest 2. Finally, we note that the closest point projection function is not unique for non-convex objects. And if you look at the medial axis of this object, you'll see a clear discontinuity along this axis. Next, let me introduce you our construction of differentiable Coronoids by addressing these problems one by one. Fortunately, they already had a solution for our first problem. In 2022, Maida and Levine proposed their LSE distance function as a differentiable alternative of the Euclidean distance function di of x. To discuss this more, let us assign some new notations. Let d hat I of x to be the signed LSE distance from the query point x to the ith object. Let fi to be the set of primitives composing the ith object oi. For polygonal objects, fi is just a set of edges. We write Maida and Levine's LSE distance in our notation, which is the formula in the middle of the screen. Notice that the LSE distance field is conservative, and hence we are only interested in the exterior of the objects. Thus, our domain of interest D will be the region where the LSE distance is strictly positive. To resolve the second problem, we find a differentiable estimation of the mean function contained in dx. We denote the smoothly approximated distance function as d bar 1 of x, which is expressed as the formula in the middle. Notice that d bar 1 of x is an overestimation of the distance function dx. Next, we solve the third and fourth problems together by proposing our self-adaptive influence radius d0 of x. That is, instead of setting the influence radius to be a constant, we want the location of the query point and its nearby objects to tell us whether and how we should modify the user-defined potential psi. First, we introduce another set of notation. Let d hat as 1 of x, d hat as 2 of x, all the way to d hat as n of x be a sorted list of the LSE distance function in an increasing order. Our motivation is that when the influence radius function equals to the smallest value between the previous constant influence radius and the second smallest LSE distance, both the multiplicative and the additive ramping strategy proposed by Chang et al. Become continuous. This construction says, when objects are too close to each other, we replace the default influence radius d0 with the LSE distance from the query point to the second closest object. Please check out our supplementary material for detailed proof. However, looking at this new formula for d0 of x, we find that the second smallest LSE distance d hat s2 and the minimum function are not differentiable. It suffices to find a differentiable approximation of d hat s2 and a minimum function, and then we are done. But how? Let me introduce here min k-sum. The idea of min k-sum is inspired by a paper called on max k-sum, where the author proposed an LSE-based differentiable approximation to the sum of the largest k elements in a list. In our case, we want to approximate the sum of the smallest k elements from an unsorted vector of LSE distances. Here, we look at some special values of k that will be helpful for our problem. When k equals to 1, we are approximating d hat as 1, which is the smallest LSE distance. Notice that the min1 sum is nothing but the LSE approximation of the main function. When k equals to 2, we are approximating the sum of the two smallest LSE distance. We denote the min2 sum by d bar 2 of x. Notice that since min k sum is a generalization of the LSE approximation of the main function, one can prove that the min k sum is in fact an underestimation. Here, our differentiable approximation to the second smallest LSE distance function d hat s2 is the difference between the min2 sum and the smooth approximation of the distance function d of x, which we previously denoted as d bar 1 of x. As the final step, we replace the minimum function using the min1 sum, which is exactly the differentiable LSE function, and therefore we obtain our self-adaptive influence radius. Now, I would like to make some quick comments for this design. Notice that d bar 1 of x is an overestimation of the minimum distance function, while our self-adaptive influence radius is an underestimation of the second smallest LSE distance function. In our paper, we proved that such deliberately designed combination of under and overestimation suffices to offset the discontinuity caused by psi g of x. Therefore, we solved problems 3 and 4. And now what? Notice that until now, the original Coulomb and the multiplicative strategy are already C1. However, the additive strategy is not yet differentiable. And again, the remaining issue comes from the closest point projection function, Cp of x. Let's look at it. After carefully investigating the role of the closest point projection, we find that the key feature of this function that we ever utilized in our method is the fact that the image of the closest point projection is a point on the boundary of the objects. In fact, the closest point property is too restrictive. Hence, our problem now becomes, given a query point x, can we find a differentiable mapping, say M, such that the image of the query point under the mapping is on the boundary of the closest object? But wait, I just said we're interested in simple polygonal objects, but the boundary of a polygonal object is C0, which is not differentiable. And you'll say, there's obviously no such mapping if we are working with the actual boundary of polygons. So here's the solution. We can use the differentiable feature of the LSE distance function. We rematch and discretize the LSE boundary of the closest object to the query point x. When we say the LSE boundary of an object, what we really mean is the isocontour such that the LSE distance function outputs 0. I will also call it the zero isocontour of the LSE distance function. Since the LSE distance function is differentiable, then its zero isocontour is also differentiable. With the issue of the see zero polygonal boundary resolved, let us go back to our question, whether such mapping M exists. The answer is yes. It's the Schwarz-Christoffel exterior mapping. Then what is a Schwarz-Christoffel exterior mapping? It is the composition of a Schwarz-Christoffel mapping and a Mobius transform, where the Schwarz-Christoffel mapping is the biholomorphism guaranteed by the famous Riemann mapping theorem. We discussed in our paper that the Schwarz-Christoffel exterior mapping is almost everywhere biholomorphic, except the prevertices on the boundary of the complex unit disk and the origin. Please check out our paper for more details. Now, let me introduce you our three-step algorithm based on the Schwarz-Christoffel exterior mapping and its inverse. Imagine the 2D Cartesian coordinates as a complex plane, and we thus have a complex query point location. We first use the inverse Schwarz-Christoffel exterior map to send the complex query point to a point in a unit disk, say W. Then we scale W to W prime, which is epsilon close to the boundary of the complex unit disk. We do not scale it to the boundary since the prevertices are on the boundary and are not differentiable, and we want to avoid that. Finally, we send W prime back to a point that is epsilon close to the LSE boundary of the polygon. As previously I said, we're only interested in the exterior of the objects, since this epsilon close is acceptable. Please check out our paper for the proof of differentiability of this algorithm in R2. Now, I have discussed everything about the differentiable kernel scheme itself. Then the next question will be, how good is it? Let us flow passive particles in flow from left to right and compare our differentiable scheme with all previous approaches. We see that all previous methods have different kinds of artifacts, and particles do not flow naturally due to the discontinuity and non-differentiability. Now, we apply our differentiable method on more user-defined potentials that are still continuously differentiable. And our method works well. We're very excited to see the future improvements of this work, and here we propose a few. We believe improvements can be made on numerical Schwarz-Christoffel exterior mapping. The current MATLAB Schwarz-Christoffel exterior mapping toolbox is unable to accurately calculate the Schwarz-Christoffel exterior mapping for a polygon with hundreds of vertices in a reasonable amount of time. Also, the computation is relatively expensive comparing with other components of our work, such as the LSE distance function. Secondly, we are curious about the extension of the differentiable kernels for 3D fluids. While the smooth approximations to the mean function and the self-adaptive influence radius can naturally be generalized to design 3D fluid flows, we do not yet have a differentiable alternative of the closest point projection in 3D. Moreover, we hope to optimize our implementation. For example, it is possible to introduce the parallel programming strategy with respect to particles on the GPU. Now, I would like to make a final summary for this presentation. We introduced differentiable kernels in this presentation, which is a C1 differentiable procedure method to animate 2D flows. Our procedure method allows users to sculpt their own flows explicitly, and the differentiability feature enables us to generate mathematically and physically reasonable animations with fewer artifacts. Last but not least, I would like to thank the University of Waterloo, the Natural Sciences and Engineering Research Council of Canada, and my co-author Christopher Batty to support this project. Thanks for watching.
And do we have Xinwen online?
Yes. Can you hear me?
Yes. Hi. How's it going?
Good.
Okay, I'm
Good. How are you today?
good. Yeah. Oh, great. Now we can all
Yeah.
see you. I don't know if you can see us, but we can all see you.
Yes, I can see you guys.
Awesome. So are there any questions? I guess I'm going to start. So first of all, the last two papers on this are 15 years apart. How'd you get started?
Yeah. So what do you mean by how do I get started? Like,
No,
thinking
this is
why
not an active. This is not an active field of research, right? Like you had this idea. How did it come up?
Well, but actually, differentiable method is kind of a kind of active research area, but maybe not procedure method these days. So we are thinking about like there works about differentiable approximation of like integration and several other areas of making differentiable schemes. And we just think about we have this Kronos paper in front of us, and we think we observe some discontinuities between in the original design, and we notice that because to get the velocity field by zero design, we need to take derivatives, and it is very natural that if you do not have a differentiable scheme, then your derivative will be not mathematically and physically reasonable. So that inspires the work that like inspired ideas that we want to make it a differentiable method and to try to see if we can make some improvements on the visual artifact, on the visual effects.
Any other questions? Yeah.
So you can also solve a similar problem by using like a panel method or some other actual solution to the flow field. Is that something that's just too computationally hard these days, or maybe it's something you could use as ground truth? Like if you just actually model those flow fields using source and sink potential field primitives, then you can often represent the shape that you want, but it's guaranteed to be not only differentiable but totally solvable.
So are you referring to some like simulators?
Yes, like people would do a flow simulation. I mean, they do this all the time in aerodynamics. That's how they model airplane wings and so on.
Yeah. So the purpose of such a design of differentiable procedure method, but not like a differentiable simulator, is that we want to give our users more degree of freedom to let them edit a flow.
Okay.
But not like simulators that will only output the whole simulated solution as the final step. So with a procedure method, like you can modify each of the steps and to get the flow you really want.
Yeah, every change to the simulation affects every other part of the field. So yeah, it's not locally editable. Okay, thanks.
No worries.
Any other questions? Okay, so I have one last one. So what do you think it takes to put this into any kind of simulation framework, right? Like if users can sketch with us right now, what do we need to change in modeling tools to have this as part of a game engine?
I think there's a relative work about this very recently in last year's SIGGRAPH, also by our group, where this work is actually inspired by zero method, where they kind of add this procedure method to their simulators, and you can refer to that.
Okay, thank you so much.
No worries.
Okay. Awesome. Our next paper also, the authors are not in the country because of visa issues. And this is a paper about modeling tube-like forms with B-splines, and the name is like the name sounds like a gangster rap line. It's like G2 blending ball B-spline curve by B-spline. It's like, say that fast now. And it's presented to us by Yuming Zhao. Sorry, yes, Yuming Zhao, Zhongke Wu, and Xingse Wang. Go ahead.
Hello everyone, I'm Yuming Zhao from Beijing Normal University, and I'm honored to share our work in this conference. The title of our work is G2 blending ball B-spline curve by B-spline. First is the general overview of our work. We use BBSC to represent tubular objects, and we have studied for the blending problem of BBSC, and we applied it on the repair of vessel branches model. Next, we will introduce some prior knowledge, mainly including the introduction of BBSC and the description of the blending problem. First of all, what is BBSC? Simply put, it is a method for modeling free tubular objects based on skeleton lines. The radius at each point on the skeleton line is calculated by the B-spline basis function to obtain a B-spline curve with the radius. Because the control balls are used instead of the control points, so we call this modeling method as ball B-spline curve. The ball B-spline curve has many excellent properties, such as it is a solid model, and we can express the physical or material properties of any point inside the model if we want. In addition, the ball B-spline curve inherently comes with the skeleton line information, which will facilitate calculations related to the dynamics. What is the blending problem? Here we gave 5 examples, each consisting of 2 BBSC. It can be observed that they can be understood as a whole BBSC with partial deficiencies. The goal of the blending, as indicated by the red line, is to use an additional curve to connect the 2 given curves, ensuring continuity and making the completed overall curve more natural and smoother. Below is a set of the examples of our method. The right part is the blending part. After the introduction of the prior knowledge, let me briefly introduce the main motivation of our work. For the previous BBSC blending method, there are 2 main features. First, it tends to use the ball-bezier curve as the modeling method for the blending part. The ball-bezier curve is similar to ball B-spline curve, except that the Bezier curve is used in the skeleton line part. Bezier curves are less expressive than B-spline curves, and the same is true for ball Bezier curves. In addition, the skeleton line and the radius are usually optimized separately in previous work. Both of these features are for the simplicity of the optimization calculation. Ball Bezier curves are simpler to compute compared to the ball B-spline curves, and considering the skeleton line and the radius separately will also provide convenience for optimization. However, this has disadvantages. Firstly, the solution space for the blending part is relatively small due to the Bezier curve expression ability is low. And the smoothness of the obtained blending curve is naturally poor. In addition, since the skeleton line and the radius are considered separately, their consistency will maintain less well. Our method is improved from these 2 perspectives. Firstly, we adopted the ball B-spline curve as the modeling method for the blending part instead of the ball Bezier curve. In order to provide a large solution space and obtain the BBIC blending path with a better smoothness. In addition, we optimize both the skeleton line and the radiance by considering the control balls as points in the 4-dimensional space. Such an approach can keep the consistency between the skeleton line and the radiance well. The figure on the right shows the comparison between the set of the previous methods and our method. You can see that there is a relatively big difference in the right blending part, and the blending part obtained by the previous method is less natural. In following, I will introduce the main method of our work, which is divided into 3 parts: strain energy function, continuity condition, and solution. First, the strain energy function. We refer to the definition of the strain energy function for general curves, and gave the definition of the strain energy function for ball B-spline curves. Just like the motivation mentioned before, we considered the control balls as points in a 4-dimensional space. Then the ball B-spline curve can be considered as a parametric curve in a 4-dimensional space. And we can calculate its curvature in this space, and we can also obtain its strain energy function. The advantage of this definition is that both the radiance and the location of the control balls are considered, not only to reflect the change in skeleton line of the ball B-spline curve, but also to consider the change in the radiance. We give 3 different BBIC strain energy samples. We can see that in this skeleton line, it's consistent. If the radiance change is also consistent, then the strain energy should be the same. In the radiance change is not consistent, the strain energy will change, which shows that the definition is reasonable. Next is the continuity condition. Previously, we have shown how to find the derivative and the curvature of the ball B-spline curve. For the continuity condition, we use G2 continuity as the continuity condition because in the most tasks, G2 continuity can already satisfy the requirement. For the blending part, we require that the G2 continuity condition is satisfied at both the first and the last connections. This can be expressed exactly in the form of the figure. Finally, for the solution part, the blending problem can be reduced to a constrained optimization problem for the BBIC strain energy function. However, there are still some difficulties in solving the problem. First, there are too many parameters to be optimized, including the 4 continuity conditions of the degree of freedom parameters and the control balls. Too many parameters can bring great challenges to the optimization algorithm. In addition, the common calculation method of the B-spline is the Debord-Cox method, which is an iterative form of the method and can bring difficulties to the optimization. We need a non-iterative form of the expression to solve these 2 problems. To solve this problem, we introduced the matrix expression of the B-spline to transform the BBIC expression in iterative form into a non-iterative form. At the same time, we can transform the strain energy function from a form that integrates over the curve into a discrete expression about the control balls. And only the dot product and the summation of the control balls are needed to obtain the strain energy function, which provides a very great convenience for the optimization. Further, in order to reduce the number of the parameters to be optimized, we first derive the control balls so that the derivative is 0. In this way, we are left with only 4 parameters of the degree of freedom in continuity condition, and this time it is convenient to find the gradient of the strain energy function with respect to these 4 parameters so that the various optimization method can be applied conveniently. Next is the experimental part, where we performed 3 experiments. In the first experiment, we compared the blending effect of the previous method with that of our method, using a 3-segment and 4-segment. It is important to note here that because of the continuity condition, the blending part needs at least 6 control balls, which is equal to the 3 segment. We compared the 3 results and find that our method is clearly better in terms of the strain energy and winding number. And moreover, the 4-segment performance better than the 3-segment, proving that our idea of finding a better solution by expanding the solution space is reasonable. In the second experiment, we compared our method with the previous method on more complex samples. We can see that our method has a clear advantage in terms of the strain energy, and the results are more natural in terms of the perception of the specific samples. In terms of the winding number, the advantage of our method is not obvious, which may lie in the sample, probably due to the smaller angular torsion of the sample. In the third experiment, we conducted the application experiments on vessel branches repairing, and the results show that our method can perform natural repair on the vessel branches, and it takes a very short time and can be done in real time. So here comes to the conclusion. In this paper, we propose a new BBSC blending algorithm. We have 3 main contributions. First, we use B-Spline instead of the Bezier as the modeling method for the blending part to obtain a larger solution space and achieve results with better fairness. And the second, we considered both skeleton line and the radius. The control ball is considered as a point in the 4-dimensional space, which is involved in the blending process at the same time to obtain the consistency of the control ball position and the radius. And third, we propose a 2-step optimization process to reduce the complexity of the optimization problem. The number of the parameters in the second optimization step is controlled to be constant 4, which avoids the optimization difficulties caused by the amount of the parameters. So here's all my presentation. Thank you for your patience. Thank you.
Thanks so much. And do we have Yuming? We can't hear you. Can you unmute? Can you hear us?
Yeah.
Okay, awesome. Yeah, so thanks so much for a really interesting paper. And we're so sorry that you're not here. What time is it over there, by the way?
About 6. I'm a little tired.
I'm sorry? Very early. Very early. Okay.
Yeah. About 6 a.m.
Okay. Very sorry about that. Do we have any questions? Okay, so I'll start. Do you see any way to generalize like the spline part, the B-spline part? Do you see any way to generalize that sweeping on other shapes that would also cause like some optimization improvements, like you did with the B-spline ball?
You mean the other methods actually for the B-Spline curve and the research on it is the model is small.
You know, I'm thinking of something like, you know, ribbed, or something like a, you know, like tracing a star shape along that and also twisting that, right? So it's gonna have optimization problems like in more than just like a smooth domain.
I see. But right, you are right. But this problem is not the key point in our paper. So I'm sorry, I'm not thinking about it.
Okay. Do you have? I see you already did some experiments. Do you have any application in mind? You mentioned modeling blood vessels.
Yeah. Such as the blood vessels and the plants, such as leaves and some fruits. We have the experiment on it, but consider of the length of the paper, we didn't put it in the paper. But we have experiment and applied it on other models. Yeah.
Any other questions? Okay, thank you so much for getting up early for us.
Yeah, thank you.
Okay. So this concludes our dynamic session, which is the last session of the day.